In this video, we'll briefly talk about some of the basics of molecular shapes. And we'll be using kind of a very basic kind of way to think about molecular shapes called VSEPR, which is valence shell, electron pair, repulsion. But it's pretty simple. There are just a few assumptions. The basic assumption is that electrons, paired electrons around the nucleus of an atom will repel each other, right? Because negative things repel negative things. So if I've got a molecule here, let's say it's bonded to four things. So this could be methane, perhaps, the carbon in the middle and four hydrogens. Well, when we draw it on a piece of paper, we often draw it as like a cross, as so they're all 90 degrees apart. But because the paper is two-dimensional, we can't see what the more likely three-dimensional shape would be, which is called a tetrahedral. And a tetrahedral is actually a much better shape for CH4 than having a kind of 90-degree angles all in one plane, because in the tetrahedral shape, they can be 109-ish degrees apart. And kind of the basic assumption here is that the electrons shared here, right, this kind of stick here is representing shared electrons. The electrons over here and the electrons over here and the electrons over here are all repelling each other. And the molecule is going to have the shape of kind of least repulsion. It's going to minimize that repulsion. So they're all going to kind of run away from each other in a way. Now the same is true for lone pairs. So say I had something more like this. 3 bonds in a lone pair. Well, more or less the same thing will happen. That lone pair of electrons will also repel the electrons shared in the bonds. Now, this applet is actually a little bit off from what I would want, because the lone pairs, these unbonded electrons, should actually have a stronger repulsive force. And those lone pairs should occupy the places of kind of minimal repulsion because they're the strongest. And you can think about that as the lone pairs are being pulled in closer to the nucleus, so they'll have more of an effect. So that's the basics, and let's kind of run through some examples. And again, this applet isn't perfect, but I can kind of explain what I'm going for. So let's look at, okay, so here's methane. And again, it has a tetrahedral shape. Carbon dioxide is actually linear, right? It's only got 2 pairs of bonds, so it's linear, because that's the furthest they can be apart, 180 degrees. And just kind of for reference, this VSEPR model uses something called steric number. And steric number is just kind of the numbers of paired electrons. So that's either a pair of electrons in a bond or a lone pair of electrons. And for multiple bonds, like a double bond or a triple bond, you count that as kind of one pair, because it's bonded to one thing. So you have carbon dioxide, we did methane. So let's look at what happens when we replace, here we go, when we replace one bonded thing by a lone pair. So this would look a lot like methane, right? There's steric number of 4, but instead of having 4 atoms bonded to the central atom, it's 3 plus a lone pair. And if you remember, the angle for methane is about 109, a little over 109. And here, it's noticeably less. Not a whole lot, but noticeably. And that's because, again, these electrons in the lone pair will actually have a greater repulsive force. So these shared electrons will kind of be squished together more to kind of give this lone pair more space, so to speak. And we can take that even a step further and say what happens when not just one, but 2 of those things in a steric number of 4 molecule are lone pairs. So this is water, and again, you can see that it resembles that tetrahedral in a way, but it's actually got a much smaller angle between those 2 hydrogens and the oxygen. And that again is because these lone pairs have a greater effect than, say, 2 hydrogen atoms would. So that's going to push these hydrogen atoms together a little closer to give these lone pairs a little more room. And I think that's all we're going to talk about. The other ones aren't going to be very familiar to us, but again, if you had 3 things, the trigonal planar 120 degrees Celsius would be the lowest energy shape.